Hello, welcome to this video, especially to Owen Dorsey. Again, thank you for commenting and asking a question. So this video is how to use lerp, a lerp function or linear interpolation, to blend tiles that you're making up a terrain with using Perlin Noise together if they have very different amplitudes or like heights, because you might have an amplitude of say 24 on this tile, and then at this part of the terrain you have an amplitude of 3, and when they meet you just get a sheer cliff between them. So it'd be nice to kind of blend those together so you get a smooth continuation across your terrain. So you could use your frequencies or different frequencies to have like a different kind of biome. So this is another way to have biomes, or an additional thing that you could use. This was Owen's idea, to have different biomes. And so this follows nicely from the previous video where we had a look at biomes. And so I've got a top-down view here, and we can see that in the north we've got some like tundra or ice. We've also got in the south we've got trees and things we can grow, and we've also got like dark green for like lowland grass and brown. And I've got a northwest tile, northeast, south, southwest, southeast, and everything looks okay from this perspective, but actually I've got it orthogonal. So if I just look at the ordinary perspective, you can see things are quite strange. So what's gone on is what I've just described, is that over here we haven't lerped between having a frequency in the north west. We've got an amplitude of 3, and in the northeast we've got an amplitude of 24 in terms of height, and so we create a sheer cliff. Looking to the south though, I've switched lerp on. So here, southwest, again we've got an amplitude of 3. And in the south east I've got amplitude of 24, but we're using lerp to kind of stretch up those voxels, those cubes, so that they match the target height of the neighbouring terrain. And I've used, I've got lerp switched on there and lerp switched off there. So what I'm going to show you in this video is how to add your own like lerp function to match your terrain. Something we might do though, actually let's unpause while I describe this a little bit. So you can see these are two very different biomes. We've got a very, very mountainous spiky biome, and we've got a very, very low land and very smooth terrain. Remember, we can use frequency to smooth our terrains. We use in our scheme, a very low frequency number to have a very spiky terrain, and in our scheme we use a very high frequency to have a nice smooth terrain. I should really flip that, it should be the other way around. It doesn't matter too much because we know that we've made that inversion and things are working. So one downside is that if you want very, very different amplitudes and frequencies neighbouring each other, even when you've got lerp switched on, it means that your source terrain is kind of stretched up. It keeps its kind of uniform Perlin according to its own amplitude and its own frequency. But if it's neighbouring something quite extreme, it really is kind of stretched in an extreme way. So what I just do is reduce things a little bit, reduce that difference. So we can see the effect of the lerp a bit more. So we're going to switch on lerp everywhere. And so in the west, our left-hand side, let's go up to 8. So we can have an amplitude of 8. We'll keep our smoothness there. And in the east, let's go down to 12. And maybe we better increase our spikiness as well. So decrease our spikiness. So increase our frequency. Let's go to about 12. Okay. Now when we play, we should have, between east and west, we should notice a difference. Yes. You've kind of got a uniformly stretched out terrain. Actually, it's quite flat in pieces. And then, as we go over to the east, we get a very spiky and a potentially a terrain that involves much higher peaks and more variation. There we go. So we've got a mountainous, treacherous biome, and if we look back at the west, much kind of smoother, uniform terrain. And if you imagine if we had more terrain to play with, like if I had some more, I've got turned around here. There we go. Right. I'm still turned around, aren't I? Oh no, I'm looking at the east. There we go. Right. If we had some more terrain tiles going this way, that were the same frequency, same amplitude as 824 here, it wouldn't be stretched anymore. There would be no stretching. So you could smooth out between biomes even further. Sorry, that's what I was trying to say. Okay, so how am I actually doing this? So let's jump into the code. So this is my little lerp. This is my little lerp test. First, I'm going to show you a basic version that I started out with, just to give you the idea. Sorry, I've just scrolled away. There we go. So we're going to have a look at this, first of all. As always, let's zoom in a little bit so you can see. Right. So the lerp function is part of Unity's math library. We just write mathf.lerp, and it's going to return a new value between the source value and what's called a target value. Okay, so it's going to return a value between those. And how do you know how far between these two? So our source value is like the source terrain that we had in, I suppose as you're looking at me, I should go over here, in the west. And our target is in the east, and that was the higher terrain. So you've got these 2 points, and what lerp does is find a position in between those 2 points. So the question is, where in between do you want to land? Well, I'm varying that as I go across from this side, along the x-axis, so along my grid of voxels, and I've got 50 voxels there. In the previous video, I had 100 by 100. I've got 50 voxels. And so for the first voxel, I just want, between the source and the target, I just want it to be stretched up a little bit. As I go along, I want the next voxel to be stretched up a bit more, and so on. So that the neighbouring voxels are meeting one another. So you don't want, say, this final parameter which tells you how far between the source and the target you want to go. You don't want that to be 1, because that would mean 100% the way across, and that would mean your source terrain would just be lifted to the target terrain's amplitude. So what you want to do is, every time I'm positioning a block, so here I'm inside the generate terrain nested loop. So this is where we're doing all the octave stuff with our Perlin Noise, as in the previous videos. And then before doing the biome stuff, which we do here, we're changing the value of y that we've decided with the Perlin Noise. So we generate our terrain's Perlin, and we generate the Perlin next door. I'll go around this way. and then we say, okay, let's match the source's terrain to the targets. And we need to do that after we've decided the basic Perlin layout, which we do here. And we've got a sophisticated system of 3 Perlin octaves. Right. So, how have I decided the target height? All I've done here is hard code a value. I've just thought, looking at the target. Well, let's have a look. I've changed these values around. Our target is in the east, and it's 12. That's our amplitude. So I could just put 12F in here. But the trouble is, I'm adding on to that amplitude because I'm using three Perlin octaves. So I've got 1 amplitude, I've got 5 over here, altogether, 5, and then another half. So it's about 5.5 times whatever the amplitude was, which was 12. So this is about 60, something like that, about 60. And I've got 50 to go across. So this is basically 1 divided by the amount of columns that you've got. So this would be a much better way to do this. And I think I've done that down here. Yes, 1 divided by columns, and I made, that needs to be a float. This needs to be a float, this needs to be a float, and this needs to be a float. If you get any problems with this not working, it might be because you haven't typed to a float. I think I just want to, do I want to do this? No, I want to do that. Okay. Just making sure I get my brackets in the right place. So let's show you that working. So once more, lerp will return a new height between what y already was, so that's the height of each voxel, and we're doing 1 voxel at a time. The target height, which is 60, so our source is about, what was it, 8, and our target height, it's going to be 8 times 3, which is what, 24? About 24, and our target height is 60. So we're going to return a floating number between those two, and as we get across our terrain, our source terrain, we're going to travel along that distance more and more, so that the neighbouring voxels between west and east are going to be about the same in terms of height. Right, and that height is going to be 60. So our y can maximally only return 60. So if I switch off the more sophisticated version that I haven't talked about yet, let's do that there we go. Let's have a look at what's going on. Let's see it working. Okay. Right. So our source in the west, I keep getting west and east, our source in the west is nice and flat. It can be, what was it, 8 high, 8 times 3 high. But it is being stretched. It is being stretched up to the right hand side. Unfortunately, we've still got a cliff. That's because our source target isn't high enough. So I've done some bad maths. So let's correct that. Let's try that. So did I save this as well? Yes. So let's go 160. And let's see what we get. Yeah, that's right. I'm just making sure I've got my... Yeah, that's fine. Well, I might make sure that's F. Or maybe it didn't work because I didn't floatify this. Let's just see. Okay, so that's worked, right. So that third parameter is indeed very sensitive in terms of being a float and not an integer or something else. Again, if you use 0 or 1, it's going to have no effect. So it's definitely stretched the terrain now. So we're using lerp, and it's hopefully I haven't over-explained it too much, but I have given you enough information that we're going across, or this way, no, this way, across the terrain, and for each column we're interpolating or lerping more as we approach the other side. Now here we go. So this is column 50, and we've reached a height of 60. There we go. And so I think I still have done my math wrong. I shouldn't have gone to 60. So let's just reduce that to about half that, maybe about 28. Dramatic pause. Okay, I haven't quite gone up enough, or have I? So we're in the west, going over to the east. And yes, now we've kind of matched. So our biomes have kind of blended together. Big problem though, because each of our rows, so going from along the z-axis, they should have a different target height, because our neighbouring biomes are very spiky and wavy. So we can't lerp to, I've changed it from 60 to 28. We can't just all lerp to 28. We want to lerp to what the individual heights of these voxels are, so by row. So what are those values? Well, they're worked out after we've done the applied to 3 octaves. So there's 2 ways we could get hold of those values. After our target terrain has worked out its Perlin, you could record each height for this neighbouring row, so this neighbouring column, so column 0 or column 1, going all the way down all of the rows, okay? And then you could pass that to your lerp script, and that could be the target for each individual voxel. So here you could have something like target y, and then this would be presumably an array, and you would have to load that array into here, and then you would get the individual targets. So that's one way to do it. I didn't do it that way. I did it in a much more inefficient way. I've done it in a non-optimal way. Let's just put this hard-coded value back in. There we go. So what I've done is think, how do I get those values back? I could just redo the Perlin 3-octave calculations here, but make sure that I do the target frequency. So what I've done is create a vector 2 target position. So I want a vector 2 is just a variable that holds 2 numbers. So I've used those 2 spaces to hold the x position of the target voxel and the z position of the target voxel. And so really, all I'm doing is finding the target y according to these 3 Perlin Noise calculations. Here we go. And for our x position in the Perlin Noise equations, you don't want the x position of this voxel, you want the neighbouring voxel's position. So I've stored that in this vector 2. So it's just the seed, I mean it's almost the same as this. It's the seed plus my position plus x. But I don't want x. I want you know what, I've done this slightly wrong. I want oh no, I have done this right. Sorry, I have done this right. I don't want the position of each voxel across the target domain. I just want the first column. So what I've done is store the target terrain in a public game object, and then I've got hold of the transform position x, because that will be the position of the first line. Let me just illustrate what on earth I'm talking about by playing and pausing and having a look down. There we go, right. So this is our source terrain, and this is our target. And so all we want is the positions in terms of height, but also where they are x and where they are z on our terrain. So what I've done is, for our lerp script, I've got a target terrain public game object, and I'll show you that here. So up at the top, which I'm not at yet, here we go. Right. Oh, lerp terrain. Why can't I see it? Oh, there we go. Right. So I've got a public seeding farm. So that's a type. I'm looking for a script. I'm looking for this script, because that's going to be the terrain script with all the frequency and amplitude and position information. And I'm calling it target terrain. And because it's public, it means I can just grab hold of the eastern terrain, and I've dragged that into that target terrain public game object position. I never know what to call these, like variable value space container or something. Okay. Now that I've got hold of that, I can refer to its target frequency and target amplitude. So in the start menu, all I've done, start menu, like Windows 95, in this start function, I've said my target amplitude equals the target terrains dot amp, because that just refers me to the seeding farm scripts frequency and amplitude. There we go. And really, should I not? Anyway, yep. There we go. Right. What was I talking about? Also, yep. Then, because we've got our target terrain, we can then get hold of the position of that neighboring column. So target terrain transform position equals that position there, that column there. Okay, so what's going on? So what we're talking about is this equation. So what we're gathering is, remember, the target height at each of those voxel positions on the target or neighboring terrain tile. And so although we're using the target position dot x, the z position, which counts for the rows, that does want to change, and that just wants to be the same as my position z plus z, because that just goes down the rows. So this will, because we're running these equations for each voxel on our source or our western hemisphere, then each row will get a different height depending on the height of its neighbour. So then we can use our lerp function after we've found what height our neighbour is at. So our target y has generated its value from calculating what the height will be at the neighbouring terrain. And I think I've explained everything there. I feel like I've really over-explained that. It's probably because I'm not coding it from scratch in front of your eyes. So I don't know. I might post this because at least you can see the code, and I've explained how it works. And I'll do a link. I'll make a link to this code so you don't have to type it out. But maybe you are using your own code that's kind of different. So this only works specifically for what I've coded in these tutorial videos. So I'm sorry, Owen, that felt like a bit messy. And it feels like I've taken a long time to explain something. But there you go. But it definitely works. Oh, so it's not working here. Why? Because I've not applied the new lerp. So what we were running there is the basic version of the lerp, which only took one line of code. And all you have to change, actually, to do it in the better version that I kind of talked about, you just have to change this value for each of the rows, because they were kind of like different. So as long as you can get that in there, and I suggest using an array, because the target terrain has already done that calculation. So you might as well just store the heights and pass it over to this script in an array somehow. I wish I would have done that, and then you don't need to do all of this, because this looks really messy, and it took me a long time to explain. There you go. So we've got the new version here working. Let's press play. And thank goodness everything's lined up. Okay, so we're using the same lerp function, but this time the target is derived from the Perlin Noise 3 octaves again. So that means everything is stitched up nicely and it's blended wonderfully. So we've got lots of ways that we've calculated biomes or created biomes. We've used Perlin Noise again without an amplitude, as it were. We've divided our terrain up. Oh, I've added some slight differences there, which I don't think I should talk about on this video. You can see the changes in the code if you go there. It's things like using randomness to kind of blur the edges, things like that. Okay, thanks for watching. Apologies for my explanation, that felt rubbish. Do ask me any questions if you need any, or demand that I take this video down if it's just so bad. Okay, thanks. Goodbye.